to design a linear phase FIR filter using the technique called as windowing. Okay, using the technique which is called as windowing, we have to design the linear phase FIR filter. So the first objective we have already defined. The objective is that we have impulse response of an ideal low pass filter, which is denoted as HD of n, and this HD of n is said to be infinite in duration. Okay, so we know for the case of FIR, the impulse response will be infinite in duration. Now this infinite impulse response, we want to limit it and make it finite. This is done using a technique which is called as truncation. Okay, now how to truncate, that we will discuss here below. Once again, HD of n is impulse response of a desired IIR filter. H of n is the impulse response of the FIR filter. Now, difference, as you know, HD of n is infinite and H of n should be finite. Now, if we take parts of HD of n, so as you know, HD of n will be a sequence of values which may be of length infinity. If we take selected points of n between 0 to n minus 1 and call that as H of n, then definitely H of n is going to be finite, correct? So H of n is defined like this. Its value is same as HD of n in the range n from 0 to n minus 1, and it is 0 otherwise. Okay. Now how this can be made possible, we can take the help of another function which is called as window function. Now let us call this window function as W of n, and let us define W of n to be 1 for n which lies in the interval 0 to n minus 1. Window function Wn is equal to 1 for n between 0 to n minus 1, and it is 0 otherwise. Now the plot for W of n can be shown here. Its values are 1s from 0 to n minus 1. Okay. Now if you take a sequence which is infinite, HD of n is infinite, multiplied by the finite window function, the result H of n will obviously be finite. Now you know what multiplication with 1 will do. Multiplication with 1 will retain the value only between the point 0 to n minus 1. Okay, so HD of n has any number of points. We don't care about the rest of the points. The points between 0 to n minus 1 is retained due to the multiplication with 1. The rest of the points are multiplied with 0. Hence the values, they vanish. They are ignored, right? So this is the process which is called as windowing. So take an infinite sequence. This is the ideal response of a low pass filter. Multiply it by the finite window, and the result becomes H of n, which is finite. Next, taking DTFT on both sides. Okay, so we have learned that to get frequency response from H of n, we have to take its DTFT, correct? So when you take DTFT on both sides, we get H of omega. H of omega is equal to HD of omega. The operation of multiplication in the time domain becomes convolution in the frequency domain. Therefore, we have star. So HD of omega star W, capital W of omega. So HD of omega is the DTFT of HD of n. Capital W of omega is the DTFT of W of n. Okay, so we have both these DTFT. We are convolving the two DTFTs in the frequency domain. Okay, so next we consider what is called as delta of omega. Okay, what is delta of omega? Delta of omega is said to be the ideal filter. See, ideally a filter should have the nature, okay, we are aware of the impulse response. As already I said, okay, delta of n is said to be the unit impulse function. Okay, so ideally we want it to look like an impulse. Ideally we want it to look like an impulse. Now when you convert it to frequency domain, you know, we get what is called as delta of omega. Delta of n is, say, the time domain representation. Likewise, we have delta of omega, which is the frequency domain representation. Okay. So the window function W of omega, if it is like delta of omega, then it is said to be ideal. Now we know how an ideal response will be. An ideal response, we get a very sharp cutoff, means there is hardly any transition. Okay, the time taken to go from passband to stop band is practically zero. We have very sharp cutoff. So this sort of behavior is found only in ideal. In real, we'll never get. Okay, so that behavior is mimicked by what is called as delta of omega. This ideal behavior is shown by what is called as delta of omega. So delta of omega for us is ideal. Okay, it is ideal. Now, if this W of omega is equal to delta of omega, then omega n is equal to 1 by 2 pi for all values of n. That means that it is said to be infinite. Okay, so if you take delta of omega, its inverse DTFT, inverse discrete time Fourier transform, is said to be 1 by 2 pi, and the value is same for all n, and hence it is infinite. Correct? This is what we understand. And we also know that when you have h of n, if you take DTFT, we get the frequency response denoted as h of e power of j omega, or it is h of omega in short. Okay. So similarly, Wn is time domain, W of omega is frequency domain. It's obtained by taking DTFT. Okay, it's obtained by taking the DTFT. Now, the frequency response of the rectangular window. Now, the term that we just described here, the window, is called as rectangular window. Why it is called as rectangular window? You can see the shape. The shape looks like a rectangle. It is discrete version, but still, if you look at the shape, the outline, it looks like a rectangle. Okay, so this is how a rectangular window is defined. Okay, so this is the concept of a rectangular window. The window function W of n for a rectangular window is said to be 1 for n value which lies between 0 to n minus 1, and it is 0 otherwise. Okay, this is a rectangular window for you. This is the very first window type, and it's the simplest window type. Now what happens? Let us just check it out. The frequency response of the rectangular window is obtained by taking the DTFT of W of n. Okay, by taking DTFT of W of n. Okay, now how do you take the DTFT of W of n, the window function? We know the formula for DFT TFT, so we can say that frequency response is capital W of W. This symbol is by definition of discrete time Fourier transform. We know the definition. The definition states there is a summation n between minus infinity to plus infinity. The input here is W of n because we're finding its DTFT. Okay, and then we have to multiply with the complex exponent e power of minus j omega n. So putting the value of W of n in the definition of DTFT, we obtain this particular equation. I hope it's clear. And then we have already defined window function. What we have defined? We have defined it as the value is 1. The value is said to be 1 for n which lies between 0 to n minus 1. Therefore, we can insert this value for W of n. Now what are we inserting here? We are inserting the value as 1, and the limits are strictly between 0 to n minus 1. This is where the window function has a value 1. So inserting this value, you simplify it, we end up with e power of minus j omega whole power of n. Now by taking this particular form, we can express it as a finite series. It's a finite series. Okay, a power of n, it's a finite series, and we know the solution for that is 1 minus a power of n plus 1 divided by 1 minus a. Therefore, what will happen to this equation now? The equation can be expressed as 1 minus e power of minus j omega n divided by, so why did you get that n here? Because the highest limit term we had was n minus 1. We have to take 1 greater than that. So 1 greater than that is capital N. So e power of minus j omega n whole raised to n, or simply multiply by n, both are same, divide by 1 minus e power of minus j omega. Correct? So this is what we have. And further, we can again here also, like we did for impulse response in the previous derivations, we can take e power of minus j omega times n minus 1 common. So if you take common in both numerator as you can take it common now. So when you take common, the expression, okay, you know, you get e power of j theta minus e power of j theta divided by 2j. It is called as sine of theta. Okay, sine. It becomes sine. So the numerator becomes what is called as sine of omega n by 2. The denominator in a similar fashion becomes sine of omega by 2. Okay, so this, if we take its magnitude, then it is this sine by sine, the frequency response of a rectangular window. When you plot it, it looks something like this. So what does it look like? We have W of omega magnitude that is shown here. This is the magnitude part. If you plot it, you will have one central main lobe. This is called as the main lobe, and on the side we'll have side lobes. Okay, and these side lobes, what we have, they are unwanted. We can call them as ripples. So you can see here that we have ripples. You know, ripples in the water. Similarly, here we have ripples. Okay. So the width of the main lobe here you can see it is lying from minus 2 pi to n to 2 pi by n. So can we say the width is equal to 4 pi by n? Okay. So n is said to be the order, and as we know, for FIR filter, the order is pretty high, correct? And the width here for a rectangular window is depicted as 4 pi by n. Okay. So this is the frequency response of a rectangular window. And we have briefly touched upon the concept of what is called as windowing. Okay, why do we go for windowing technique? It is to convert the ideal response HD of n, which is infinite in duration, to make it finite. So multiplied by a respective window, and what effect do we have in frequency domain, that also we'll touch upon. Okay, so this is the process. So some simple methods are there and some simple maths is there which we have to be aware of. Okay. Now let us start with the windowing technique now. We will learn, according to your syllabus, we have 4 different types of windows. We'll talk about the 4 different types of windows and we'll get to know what it is all about. Okay. So the very first window type that we will discuss is called as rectangular window. Okay. The first window type is called as rectangular window. Okay. So the window function may be given a name as WR of n. The subscript R denotes rectangular. Okay, so the impulse response of the rectangular window will look something like this. It is taken for n points. Here, just for illustration, there's a number called as 32. It can be any length. What choice you want, that many points you have to take. Okay, so the impulse response is very simple. The values are continuously ones. Okay, between 0 to n minus 1, and after that the value is 0. Correct. So this is how the rectangular window is designed. And when you take the magnitude response, see, already just a while back we plotted it. Okay, we plotted it. We saw that, okay, sine by sine, and we plotted the response. Now the response that we plotted was symmetric. What we just plotted was symmetric. Okay, so how to get, we have just seen. Okay, but the plot was symmetric, means what? We have one half, okay, that is 0 to plus infinity. There's another half, 0 to minus infinity. Correct, it is symmetric. So over there now we are presenting only the right half. So you probably got the picture, but we are just showing the right half. Okay, so when you see the right half, what does it look like? Again, you will find what is called as the main lobe. Okay, and along with the main lobe, we will have what is called as side lobes. Now, the main lobe is the one which is important for us. Main lobe is the one which is important for us. So the main lobe, you can see here, is the tallest one. Highest one what we have is the main lobe. So between 0 to some point, here we have the main lobe, and then you have many side lobes. Okay. Now the rectangular window, although it is very simple because the window function is very easy. The window function is defined as WR of n is equal to 1 between 0 to n minus 1 and 0 otherwise. So it's very easy, and multiplication by 1 anybody can do. It's an easy operation. But what is the disadvantage of rectangular window? The drawback of rectangular window is that you can see the difference between the main lobe and side lobe is not very high. Okay, the difference, the margin here is called as minus 13 dB. Okay, so if you compare here, the main lobe will have, obviously starts from 0. Okay, the side lobe here will be at 13 dB. The side lobe will be 13 dB. Okay, side lobe will be 13 dB. So what is the difference? The difference is equal to minus 13 dB. So minus 13 dB of difference is not very high. Okay. Now why are we worried about the difference? See, main lobe is what is going to pass the signal. Okay, main lobe is what is going to pass the signal. We ideally want the main lobe only to be present. Side lobes are undesirable because these side lobes will leak the unwanted signals. Okay, so if side lobe is high, it will also pass the unwanted signal along with the wanted signal. So ideally, we should not have side lobes, but we will have side lobes. Now, if you are having side lobes, we want their magnitude to be small. We want the magnitude of the side lobe to be small. The magnitude should be less. Okay. So how do you ensure that the magnitude of the side lobe is less? You have to carefully pick the window. You have to select the window. We have choices, different types of windows are there. Okay. Now the drawback of rectangular window is that the difference between the main lobe and the side lobe is not very high. We have large amount of ripples. These side lobes, we can treat it as ripples. So the amount of ripples in rectangular window is more. Now why do you get more amount of ripples? The concept is very simple. The window function that we have chosen here, which looks like a rectangle, the change is sudden. The change is sudden. What do you mean by sudden change? You can see that we have continuous ones and suddenly the value changes from 1 to 0. Because the change is sudden, it results in large amount of ripples. So this is called as ringing effect. If you have a sudden transition in your window, it results in something called as ringing effect. That ringing effect is what gives you these side lobes. Okay, and this particular phenomena is called as Gibbs phenomena. The name given for this phenomena is Gibbs phenomena. Okay, so due to Gibbs phenomena, we have ringing effect and we have ripples. Okay, we have lot of ripples. So how to reduce the ripple? The solution also lies in the problem. Because there was a sudden transition in the window, it caused more amount of ripples. So make the transition smooth as far as possible. Make the window function which is as smooth as possible. Okay, don't have sudden change. Okay, so anyway, we shall finish this topic on rectangular first. So the magnitude response, right half we have seen looks something like this, right? The difference between main lobe and first side lobe is minus 13 dB. Now, if you design a low pass filter using this type of window, let me design an ideal low pass filter using this type of rectangular window, what will happen? Okay, so if I design this low pass filter, then the filter with rectangular window will exhibit the frequency response like this. Okay, h of omega, it's in dB scale, so the frequency response will look like this. So from here you can see that the main lobe is quite wide, right? The main lobe is quite wide, and the difference between the main lobe and the first side lobe is minus 21 dB. Okay, as we already stated, it's not a very ideal case, it's not a good case, but still since it is simple, we can actually consider it. Got it? So this is the difference between the main lobe and the first side lobe, which is minus 21 dB. Okay. Now we shall summarize now. The impulse response in the rectangular window is given by the window function WR of n equals to 1. For n between 0 to n minus 1, it is 0 elsewhere. Okay. The biggest side lobe is 13 dB below the DC magnitude. You know what is DC magnitude? At frequency 0. When you consider the frequency 0, what value you have? This is called as DC magnitude. Okay. It's a DC magnitude. So between 0 and this point, the difference is how much? Minus 13 dB. Okay. The difference is minus 13 dB. Some values we have to remember. Okay. Sometimes theory question is asked to describe different types of windows. Then you have to present all these facts. Okay. And a low pass filter produced using the rectangular window should have an approximate difference of 21 dB between the pass band and stop band gains. Okay. So what we realize here, the margin between this and this region, as we said, is desirable. It's called as the pass band. And the region from here onwards is said to be the stop band. So how much is the difference between the pass band and stop band gains in the case of rectangular window? It is equal to minus 21 dB. Okay. It is minus 21 dB. All right. Yeah, so this is some information that we were able to gather about the rectangular window. Yeah, first let us study different window types, then we shall talk about problems and things later. Okay, the next window type we have is called as a Bartlett window. The Bartlett window is also called as a triangular window. Bartlett window is also called as triangular window. So compared to rectangular, somehow this shape is little smoother than the rectangular window. Is it right? Rectangle had a sudden drop. Here it is little angular but still okay. Little better. So this WB of n, B for Bartlett. Okay, Bartlett is shape is triangular window, shaped like a triangle, so it's also called as triangular window. Now here, if you look at the magnitude response, what do you observe? We observe that the difference between the DC 0 DC level and the first side lobe is minus 27 dB. There we had 13 dB, here we have 27 dB of difference, which is relatively good. Okay. Now how the window function will be for triangular, the equation is given like this. WB of n is equal to 1 minus 2 times magnitude of n minus 1 by 2 divided by n minus 1, and this we have to substitute values from 0 to n minus 1, where n is the length of the impulse response. Okay, and this is how the window function has been defined. Now let's look at some of the characteristics. We saw that the difference between the DC level and minus 27 dB is the value. Okay, now if you design a low pass filter using it, the difference between pass band and stop band this time is going to be 25 dB. So last time how much we got? We got 21 dB. So this is an improvement. Okay, the more difference you have, the better. Okay, so difference between pass band and stop band for rectangular was 21 dB. Here it is 25 dB of difference. Okay, yeah, the plot I have not shown here, but you can imagine it's like the previous one with the difference which is slightly more. Next, third type of window is called as Hanning window. The third type of window is called as Hanning window. Now let's have a look at what is Hanning window. Now compared to triangular, we believe this shape is smoother. Okay, and you can see the immediate effect. Can you see the ripples how they are? The ripples are there, but you can see the ripples is less. The height of the ripples is less. So having a smooth response is a solution. The more smoother it is, the better your response is going to be. Okay, so the difference between the DC level, okay, the DC level and the first side lobe is minus 32 dB. Okay, still there's an improvement. Okay, it is improvement over the previous. And if you design a filter, difference between the pass band and stop band is minus 44 dB. So look at the progression. First number we said is 21 for rectangular. Next number we said is 25 dB, and now we are talking about 44 dB. So it is a jump. It's a remarkable jump compared to previous. Now what is the problem here? No problem. The expression is little complex than the previous one. Okay. So the expression which you have to remember, W Han of n, the window function for Hanning, is given by 0.5 minus 0.5 into cos of 2 pi n divided by n minus 1. Once again, 0.5 minus 0.5 cos 2 pi n divided by n minus 1. And this is defined for value n between 0 to n minus 1 and 0 otherwise. So this expression has to be remembered before we can substitute and solve it. The next window type is called as Hamming window. Now how Hamming is, shape wise you can see almost same but not exactly same. Okay, it is similar but not exactly the same. Okay, so this small change, okay, so you can see at the beginning it starts little sooner, right? The height is little more compared to that of the Hamming. This is Hamming. The previous one is called as Hanning window. Okay. Now the function is called as W ham of n. So previously we remember the equation was 0.5, 0.5. Here it is small change. It is 0.54 minus 0.46 cos of 2 pi n divided by capital N minus 1. So this is the function called as Hamming window. Okay. And 0 otherwise. Now what is the difference we observe here? Now this one is pretty good, even better than the previous. So the margin we have here is minus 40 dB, 42 dB in the frequency response, and the filter response, we can see a filter designed using it will have a difference of minus 53 dB. Previous one we got 44 dB. So here we have 53 dB of difference between the passband and stop band. So this is still better compared to the previous one. Okay. So these are the 4 window types that we have. There's a 5th one called as Blackman, which is even better than this, but I don't find it in your syllabus, so I don't think it is worth talking about it. Okay. So these are the different types of windows and these are different types of window functions. Now we are set, we can actually go for designing also. Okay. Now we are aware of the procedure. We can actually think about learning the design. So yeah, just for your information, this is the next type, which is called as Blackman. Okay. This is the next type of window, which is called as Blackman window. Okay. So the equation for Blackman window is slightly more complex than the previous ones also. So the expression for Blackman is 0.42 minus 0.5 cos 2 pi n by n minus 1 plus 0.08 cos 4 pi n by n minus 1 for n value between 0 to n minus 1. So slightly more complex equation, but you can see the result here. The results are very good compared to the previous windows. Okay. So the margin we have here is minus 58 dB. Okay. And the resultant filter, low pass filter, the difference between passband and stop band is minus 74 dB. Minus 74 dB is a tremendous improvement when you compare with the previous. Okay. So yeah, so these are the different types of windows, and we have learned the different window functions also. Okay. Thank you all.